All right. Good morning, folks. Good to be here. Hey, it's almost afternoon. We passed noon. Good to be here with you. Welcome to this session here in the AI plus Art division. As you know, the plan that the folks put together is for me to give you a little bit of an overview, how we approach innovation, how we do research and technology development here in AI plus R. And I'll be very quick to allow you to spend more time with three good examples of some of the disruptive innovations we're coming up with. But I think this intro will give you a little bit of context to get those. So let me start a little bit with the punchline. The punchline is that artificial intelligence actually is a big deal. Every application is going to be intelligent. You know, a few years down the road, if you have an app and your app is not going to be intelligent in some way, learning from the user, learning from data, learning from other things, it's going to die. Every app needs to be intelligent. Everything needs to be intelligent because that's where the world is going. So we need to be intelligent. For apps to really be intelligent, you really need to have super powerful cloud processing because you can't just run very intelligent things exclusively in the device. And I don't need to tell you that. You understand the concept very well. And your cloud, to be intelligent, needs to be super powerful, and I'll tell you about that. And also, especially from a Microsoft perspective, we want to empower people and empower the community, empower other companies to deliver intelligent things. So we need to have that cloud programmable. So the intelligence is easily available for you to develop apps. So that's roughly the punchline, but now let me tell you a little bit more about that. To get to that, you really need to develop advanced technology. And a good way to do so is by having a research organization. So I'm just starting with a very historical thing, is how Microsoft Research started. Was the CTO at Microsoft at the time, Nathan Myhrvold, sent a memo to Bill Gates, and technology is changing very fast. And that was 25 years ago. Today is much faster. We need to have a research organization to be able to keep up or to push the limits. So Bill immediately accepted, the board of the company immediately accepted. Microsoft's revenues at the time were like 1% of what they are today, roughly. It was only $1 billion company. And we created Microsoft Research with the main mission of advancing the state of the art, which means it's really about pushing the frontiers of the technology. As you do so, try to bring the best results so it has a business advantage to the company. We're not an academic lab. We're close to, we operate in a similar way to an academic lab, but we're an industrial lab. And ensure the future of Microsoft in the computing field, which means push for new things, push for totally disruptive, change the game in a few things, and you're going to see examples of changing the games in the demos we selected for you today, right? So we actually can say that Microsoft Research, you're very familiar with our industry. Other companies also try to do research, but there are some unique aspects of Microsoft Research when you look at technology development in information technology, right? In computing and information technology. One of the examples is that we really have mostly staffed the research division with folks with PhDs, not just the researchers, but also the engineers, so that they can actually push the state-of-the-art, advance the state-of-the-art. We really cover the breadth of computing, over 60 different research groups. So anything related to computer science, there's some team doing something similar. And in similar areas as well, you will find folks with PhD in psychology, sociology. Look at sociology today, right? With social networks and all of that. The way people behave and groups of people behave today is very different. So sociology today, a fair amount of it is computational. So we address those together. We're all over the world, 11 separate locations for two reasons. One, diversity. We have more thinking. The other one is what we call local to global, the diversity not only of the people, but also diversity of problems. A problem that may be of high importance in India, if you solve that, or in Brazil, or in China, if you solve that, you say, wait a second, that problem might exist in the US as well, but you got the attention to that problem because you had a lab and people are more focused on that problem in some other region of the world. And this is the important part, and I will elaborate a little bit more about that, is that we think we do a pretty good balance between basic research and applied research. If you're thinking too much about return on investment, you pivot too much in applied research, you want to see returns soon, and then you miss an opportunity, especially when you're investing a significant amount of money, right? We use a small portion of the R&D funding for Microsoft, but as you know, Microsoft is spending about $12 billion a year in R&D. If we're spending that much, some fraction should be going in more basic research. It would be crazy not to do so. We do a lot of scientific work. One of the examples, premonition, for example, will show you that, where we enable other fields of science through computer science and through artificial intelligence. We also promote platforms within the academic community. We publish our work. Publishing is a great idea because you create a feedback loop where we publish lots of our ideas. The community sees what we're publishing, publishes on top of that, they develop even further. So not only the technology develops further because of the input we gave to the community, but we also see who are the researchers. We can hire the students as interns, and then later, when they graduate, we hire them as researchers, and everybody wins, right? And now, at the end here, we're part of a larger team. We recently, a few months ago, as you know well, we created the Artificial Intelligence and Research Group, where we put together a lot of separate efforts like Bing, Cortana, which have a lot of intelligence behind them, together with Microsoft Research, and we built this bigger organization. That shows you how big a deal AI is, because you imagine how much it costs to run a 6,000-person organization. You had a question.
Up here, you have agile de-risking, but I don't think I heard you mention what you mean by that.
That is a good point. Let me go back very quickly to that. The idea is that, and I'll go into a little bit of the model, but just as a first bit, de-risking means that if we think some approach, some new technology is interesting, or some new algorithm, or some new hardware, whatever it is, the advantage of having a research organization that can tackle that and fail fast and discover if that's a good idea or not, then I'm not putting at risk the development of more stable and sustainable offerings of the company, right? So I can come up with some new storage thing. If it works, and you will see one in a little bit, if it works, then Azure will say, aha, maybe I should be using that kind of storage, but I'm not going to pivot Azure on that so soon. So let's us take the risk, and if necessary, fail, and then at the right time, transfer to product. Okay, thanks for the question. So one thing that we like to say is that sometimes I mentioned the word ROI, and if you think at ROI in terms of success rate of research projects, I bet if I ask you, you know the answer. What's the success rate of a typical research project? How many of them actually work? How many of them in 3 years or 4 or 5 actually see the light of the day in a product? 5%.
Single digit.
Single digits.
Percent or 2%.
Exactly, it is single digit. If we get to 10, we're being very successful. If we were to get to 50, we're doing something wrong because it was too applied. You can't be that successful when you're doing research. But we like to pivot and ask that question. Of the products and services out of Microsoft, which percentage got a business advantage because of Microsoft research? That number, we want to be 100%. If something goes out and there was nothing from research in it, we missed an opportunity. So we don't want to miss those opportunities. So I've just put examples here of major Microsoft products, and I included one, which is an interesting cognitive services. I'll say just a few bits more about it, because it's a concept and idea in a service operated by our division. So we're actually shipping new products as well in that sense, right? So we are in a new area for research. You know the pillars of the company: reinvent productivity, the intelligent cloud, as I told you, more personal computing, which means computers now have to see, hear, understand. We want to talk to the computer in our language, like an example in the second picture there, where you just send a text message to a service and arrange for a service to be provided to you, all via text message. You don't need to install an app. You don't need to know how to install apps. You don't need to know how to operate anything. You just need to know how to send a text message, which of course you do, right? With bot frameworks and things like that. And it's the advances in machine learning and natural language processing that are allowing us to do that. So there's many ways to manage research, but we basically try to describe by mapping all of those projecting all of those to two dimensions. In one dimension, time. Is this a schedule or non-schedule? The other dimension is a focus problem or an open-ended problem. For example, if it's unscheduled and open-ended, it means I don't know what I'm doing and I don't know when I'm going to be ready. So that's what we call blue sky. And blue sky can include things like Natick, our data center in the ocean. On the other hand, if it is a schedule, I really want to ship it soon, and it's focused, it's a particular problem, we can have something like Catapult, which I'll mention a little bit, which is how you accelerate the data centers, but ship it very soon. So we have an advantage of having a more powerful cloud. It's very important to highlight that research is a long game. We need to be willing to wait a long time if necessary. For example, speech recognition. You're all familiar. Today we all use speech. We got to the point where we began to use speech about 15 years ago, where for arbitrary utterances, we had like 25% or so, which was okay for some applications. For digits, the error rate, this is word error rate, how precise you are in recognizing as it progressed over the years. For digits like the credit card number to the company, that's easy, relatively easy. The problem is you say something, anything you want for Cortana. Did it really hear you? Does it know what the words you're saying? Interpreting those words is a second problem. Let's say just the problem of hearing what you're saying, being able to pick up the words. We spent 10 years with very little evolution until the deep neural networks came in, and then there was a very rapid. And I remember at this time here, I was the managing director of the lab in Redmond. The team was mostly here. I was paying the bill, and every year paying the bill, and the improvement was not there. One day it came here, and now when you get to this error level below 10%, now you enable many more applications. And now you can say, okay, I can put speech on anything if I want, and it will work, because it's basically making very few mistakes, and the context and the conversation can fix that. In fact, a few months ago, we just won a competition where in a standards data set, we got a 5.9% error rate. To give you an idea, humans, it's about 6. So we basically achieved parity with humans. We can do as well as humans. But it took a long time to get there. Another one that I want to highlight to you is the powerful cloud. We need to be in the cloud to really be able to crunch petabytes, exabytes of data. But to do that, your cloud needs to be powerful. So we developed here at Microsoft Research this small board that we call Catapult. Have you heard of this project before? Actually, the idea was it's such a small board and it's so efficient that it doesn't need an extra fan. So you can attach that board to your existing computing blades in a data center and multiply between 2 and 50 your computation per energy. For every kilowatt of energy comes in, how much energy goes out. And now we're shipping it and it's running. We can actually, recently we demoed last year at Ignite, you can build an exa scale computing, exaflops, which means a billion operations per second. It's even hard to fathom. Just to give you an idea, if you take all of Wikipedia and translate it to another language, all the articles, a few billion words, it takes a tenth of a second to do so. Of course, that's not very interesting. Why do I need to translate the Wikipedia 10 times a second? But imagine what I can do with your data. If you're doing medical imaging or scientific application and you suddenly get a petabyte of data and I need to crunch through it, I can probably crunch to it very quickly. But it takes hardware investments to get there. And in fact, just a couple weeks ago or last week, GeekWire called it the Innovation of the Year of 2017. The key advantage was to use FPGAs, which is a different kind of processor. So a chip can have hundreds of thousands of cores in it, much simpler cores, but they are very good for doing the machine learning algorithms that allow us to do translation, speech recognition, and other things.
That was kind of like the question. What are some of the, I mean, FPGA has been around for a while, but what are some of the practical applications for enterprises? Because there's not so many people that can actually program an FPGA efficiently.
Exactly. And then that comes to the next point where we try to put those things under an API that allows you to have access. So you don't need to actually learn to program an FPGA. You can just use as libraries to run, for example, deep neural networks that are running on the FPGA, but you don't need to know exactly how. You just need to know the basic structure. So in cognitive services is an example where you can send a picture to cognitive services and we come back to you with a potential description of that picture. Computer vision is not exact, so the description is not going to be 100% correct. But it may be good enough for you to index a data set of pictures. Your business may have generated, 10 million pictures, and you don't have full descriptions of them. Send them to cognitive services, and you might be able to create new indices and have better access to those pictures. You can do emotion analysis on faces. For example, in a picture, recognizing that there is a person is easy. Now, we can go further and say, not just that there is a person and potentially who is the person. We run Windows Hello by recognizing who is in front of the computer. But now I can tell you the emotion. And you can see, what do you do with the emotion? Yeah, for example, you're in an ATM. You're fiddling with the ATM. Something's not working. You're making funny faces. An alarm goes up inside the store or the branch, the bank branch, for example, and somebody comes in and says, are you having difficulty? May I help you? So you can produce different levels of service by having those.
Are most of these projects or services based on unsupervised learning? What do you do in the area of supervised learning? Do you have the equivalent of like Amazon Mechanical Turk to enable crowdsourced labeling or training data sets for these kinds of projects?
Yeah, there's many approaches. You can use crowdsourcing as well. We have more on the supervised learning side where you actually bring training data and we crunch through your training data. And there are ways to extend that with unsupervised learning as well. Right? But usually crowdsourcing can be good for some problems, but more and more you're getting problems where data is being generated automatically at a very fast rate. So you need to be able to process very quickly, and ideally with a little bit of supervised learning to at least bootstrap. Right?
How would you say you're dividing your efforts between, something like an FPGA and a supervised? Because they're very different problems, but your research is more focused on the fast, brute force of like applying power to a problem, or crowdsourcing?
In most cases, you actually need to apply power because it's the kind of data, for example, for Internet of Things, data from sensors that you will see in some of our demos, where you really don't have an option to crowdsource. It really has to be processed in a different way. But also we know the FPGA is not necessarily best for every single. So we have an architecture where we use classical CPUs, we use GPU acceleration, and we also use FPGAs. But now we have different trade-offs in complexity.
So you're more focused on, if you take a spectrum of people-based training and classification to, brute force. I mean, where does Microsoft? I'm sure you're across the whole spectrum. But
yeah, basically it is across the whole spectrum, and depending on the application, you can use all of them, right?
It's also a good question on the cognitive services, applying those within the context of the APIs and SDK. So as developers are learning how to use these capabilities, a lot of people are wicked inexperienced with this, right?
Right.
So how are you leveraging cognitive services to enable people to do better cognitive services and incorporate that as both as part of their development and then the life cycle, because quality and change management, all these things change, and deployment planning and architecture has to change too when you're deploying in these more complex environments.
That is true. So what happens is that some of the basic services like text analysis, computer vision, the APIs that are very high level, you send me a snippet of audio and I can do some pattern analysis for you. If the audio has text, I can recognize the text for you. I can translate. If the audio has speech, I can recognize the speech, convert to text, translate the text, and do those things. If you need to go to a lower level, when you want to be able to design your own, let's say, algorithms and things like that, then we do provide CNTK and other platforms where you can actually program at a lower level. And assuming you're running all of that in Azure, we have a whole Azure machine learning stack where you can visually program those modules at different levels. So you can start with cognitive services where it's almost black boxes. You just put your data in, we give you some results, and you can dig in as much as we want, and we provide several layers of APIs to do that. Right.
That sounds great, thanks.
Where are you incorporating generative adversarial networks into this entire framework? Because those are really hot right now in terms of.
You know, that's one of the many hot kinds of machine learning algorithms, and we try to be on top of that. I can't give you a precise answer to that one, but we can follow up with that. Yeah, but we're always running different kinds of algorithms because it's the nature of our machine learning research, right? All right, with that, I think I will stop. And yeah, you guys now, we selected 3 very good demos: DNA storage, whole internet in a shoebox, NUI graph, visualizing well gigantic amounts of data, and premonition, finding mosquitoes and detecting outbreaks. So that's one, for example, where we push the limits of science in there. All right.